everything that we're talking about relates to what we've previously talked about. And one thing that I want to show with that, so one of the new Jamboards that I made was looking at the receptors. And so in the middle of the Jamboard, in the middle frames, I have our previous one where we talked about the pharmacology of stuff, or technically the synaptic signaling. We used this figure, and we also used a version of it when we talked about the pharmacology. And so I want to come back to this picture because when we talk about the neurotransmitters and we talk about the receptors, we get into a lot of details. And you'll see there's quite a few hectic details in some of the receptor charts. But it all comes back to the signaling at the synapse right now. And so what I've done is in the middle of this, I kind of have the neurotransmitters and the making of the neurotransmitter. And so the synthesis of the neurotransmitter and the reuptake of the neurotransmitter. I left the completed forms for the neurotransmitter chart. And then for once the neurotransmitter gets into the synapse, right, it binds to that receptor. So all the receptor chart that we're talking about coming up is all happening right here. So in that postsynaptic membrane, when the neurotransmitter binds to the specific receptors, this is where we are zooming in for these particular charts over here. So just to keep in mind that all of that is related to each other. And then if you take, well, I think on yours where I have it for the student one, this one's the answers one. Here we go. Let me get to the student one. Oh, no, that's the wrong one. I don't have it pulled up just yet. What are we going to do? Yeah, okay, here we go. So I did put on yours. I forgot to change it on mine. But so just circling this step where the action potential comes down, opens the voltage-gated calcium channels to cause the release of the neurotransmitter. That's all the action potential chapter. So I know that it isolates these things into each chapter. And you're like, okay, I did that chapter. Now I'm done. I'm going to move on to the next chapter. But always keeping in mind of how these things relate to each other. So taking a zoom out and looking at the big picture every time. So when we look at, when we go and move into this receptor chart, it is beneficial to also go back and look at the neurotransmitter chart, because what we will be talking about is for the receptors. Actually, let me go back to the one more. There we go. When we talk about the different neurotransmitters and how they are excitatory or inhibitory, or some of them are both, this is where we get into the activity of the receptors. So the positive or the excitatory and inhibitory input that these neurotransmitters can have are because of the receptors that they are binding to. So this entire column here is what we're doing for the receptors. We're basically taking a zoom in on this column and looking at the action of the neurotransmitter onto the specific receptors to give a specific response. So keeping that in mind, we will move into the neurotransmitter receptors. So what I want to kind of clarify is that on this one I give you this because it's very hard it would be very difficult for you to come up with these on your own. So I'm giving you these, but then later I do want you to know these. So this is something that you kind of just have to memorize. This one is whether they are those ligand-gated channels or those G-protein coupled receptors that we just reviewed. And then if they are a ligand-gated channel, they're going to be permeable to something. So you can technically logic and reason the answer for this from this, and then you can also technically logic the excitatory or inhibitory effect for each receptor from what you're seeing here. So in the end, for an exam, you do not have to memorize this column, right? I want you to, right now, use this column in order to be able to predict what you should put here and what you should put here. So I'll start with the first one and then I'll let you pause. But you're thinking about that ligand-gated channel, right? An ion is going to go through. So it needs to be permeable to a particular ion. A G protein coupled receptor is not going to be permeable, but it is going to affect different channels. So if you look at this first one, you see that it is permeable to sodium and potassium. And so that indicates that an ion is moving through it. And specifically, it is permeable to potassium, but it's technically, I've highlighted it and made these bold, it is selective to sodium. So you can kind of just say it's selective to sodium. Keep in mind that potassium can go through, but not as much as the sodium. So for your channel type, or for your receptor type, if it's permeable, it has to be a ligand-gated channel. That might make this a little bit easier. If it is permeable to sodium, if you remember where sodium is more concentrated, it is more concentrated outside of the cell. So that means that sodium, when the channel is open, sodium is going to come into the cell. That's a positive moving into the cell, which would be exactly excitatory. So hopefully that helps you figure out what type of channel it is and whether it's excitatory or inhibitory. And then, again, I would not make you memorize these, but based on the action of the drug, you should be able to reason whether it's an agonist or an antagonist. So something that's going to block the specific neurotransmitter release, right? That if you're blocking the release, that means the neurotransmitter is not going to get into the synapse. So that means it's an antagonist. All right, so now, hopefully armed with that, what you can do is pause the video and go and put these where you think they should be. And then just as a note, there is a second page for this. So the new ones on there, this one goes acetylcholine, glutamate, and GABA. But then I have two more on the bottom that didn't fit on there. So you get more practice again if you want to do the glutamate and the GABA. But then the new ones on this page are norepinephrine and serotonin. So just a continuation of the same chart. So pause the video, go see if you can fill those out, and then I will come back and give you answers. Okay, let's see how successful you were. So this one closes leakage channels, so it's got to be a G protein coupled receptor because it's not permeable. This one opens potassium leakage channels. This one is permeable, so that means it's got ions moving through it, so it's a ligand-gated channel. Same thing for AMPA receptors. And then M-GluRs decrease potassium conductance, so that means they have to be a G protein coupled receptor. And just as a hint, anything that says M, this M stands for metabotropic glutamate receptor, so that already technically gives you the answer for that as well. This M over here stands for muscarinic, but you can also think that they are also metabotropic, just by the M. All right, the GABA receptor is one that the GABA A is a ligand-gated channel, and GABA B is a G protein coupled receptor, so I'm wondering if I have this without enough GPCR. So I'm going to change this. It'll be changed on yours too. All right. So hopefully you were able to see, right, the G protein coupled receptors affect but are not permeable to these. The ligand-gated channels allow the ions to go through, so they are permeable to each of those. All right. And for the effect on the membrane, so closing potassium leakage channels, right? Potassium leakage channels allow potassium to leave, so that's a positive leaving, but if you stop that, then you're stopping a positive leaving, so that is excitatory. And then opening potassium leakage channels, that is inhibitory. So this is where we get, oops, too far. So this is where we get that acetylcholine having the effect of both excitatory and inhibitory because it can bind on different receptors. So cool. So same neurotransmitter having a different effect because of the different subtype of receptor that it's able to bind. All right, so NMDA receptors, they're permeable to all the cations or all the positive ions, but they're more permeable to sodium and calcium. And sodium and calcium are both positive ions concentrated outside of the cell. So when you open a channel for sodium and calcium, they're going to come in. That's a positive coming into the cell, and that is excitatory. And glutamate is the main excitatory neurotransmitter, so most of them are going to be excitatory. I will show you something a little bit weird that happens here. NMDA receptors, definitely excitatory. AMPA receptors are also permeable to all cations, but more selectively to sodium. So again, that's sodium coming in. So that's going to make or depolarize that cell. That is an excitatory response. The metabotropic glutamate receptors, if we go back to here and our submitted questions that we looked at and to here, right? These are the glutamate receptors, and you can see how many there are. So there's a lot of them, and so I've only generalized within the Jamboard just the main ones, right? And those decrease potassium conductance, so that's decreasing potassium leaving the cell, right? And so that is going to be excitatory. Now, I do want to put in a disclaimer that there are multiple metabotropic glutamate receptor subtypes. And so I'm going to bring in, just so you recognize, because when we look at the vision chapter, we'll see a metabotropic glutamate receptor that is inhibitory. So I don't want you to be just shocked because I've said glutamate's the main excitatory neurotransmitter, but glutamate can also be inhibitory because of the different subtypes of the metabotropic glutamate receptors that it can bind. All right, so GABA, I can just guarantee you, is always inhibitory. So if it's permeable, if the GABA A receptor is allowing chloride to move through, chloride's more concentrated outside the cell, so it's going to move inside the cell. That's a negative moving inside. That is inhibitory. And then the GABA B G protein coupled receptor opens potassium channels, so that means a positive leaving. And it closes calcium channels, so now you're preventing a positive coming in. So that is also inhibitory. And then anything that stimulates a receptor is an agonist. So both of those are agonists for the NMDA and AMPA receptors. And then if you block the receptor, then that's going to be an antagonist. So hopefully you took the time to go and do both of these. I will just go to my answer key because it'll be faster for me, but because these have already been, you should have already filled those out. And then for these, I'll just explain it to you. So get to my answers. All right, so glutamate and GABA we just did. And then, so norepinephrine, right? So increases, so norepinephrine and serotonin, they're all metabotropic receptors or G protein coupled receptors. So you just have to know that they're always that. There aren't ionotropic receptors or ligand gated channels that are that have norepinephrine and serotonin as neurotransmitters. And so for norepinephrine, it's going to increase calcium, so that's a positive inside the cell. That's going to be positive. Same thing for the other subtype. So they're doing very similar things. Serotonin, you go back to the neurotransmitter chart, you recognize that that one said it was both excitatory and inhibitory. And this is why, because the 5-HT1 subtype of the receptor increases potassium permeability. Again, potassium leaving the cell, so positive leaving the cell, that's inhibitory. And then the 5-HT2 receptors increases calcium. Calcium coming into the cell is excitatory. And then if we are going to, I'm just going to start with down here. Actually, no, I'll do this one. So this is going to block the autoreceptors. And if you remember, the autoreceptors feed back to prevent the release of the neurotransmitter. So the autoreceptors are themselves inhibitory or a negative. And now we are blocking that negative to allow it to be positive, right? So a negative blocking the autoreceptors, but the autoreceptors are preventing the neurotransmitter from coming into the synaptic cleft. So we block the block, then that's an agonist. Same thing for the reuptake inhibitors. So these selective serotonin reuptake inhibitors block the reuptake of serotonin. So that means that serotonin is going to stay in the synapse longer. So this is an agonist. And then anything that stimulates the receptor mimics the receptor, and that is also an agonist. So that is the neurotransmitter chart. And then what I also have is because I don't want you to be able to reproduce this, I just wanted you to use this as a tool in order to understand over here and over here. And so what I've done is I've also given you, except I don't want to show you the answers yet, so I've also given you the chart in a way that you would need to be able to reproduce it on an exam, right? So what you need to be able to do, I had given you this before, but now you should have a better idea of where these are going to go. And then without those clues, I need you to be able to recognize which ones are ligand-gated channels and which ones are G protein coupled receptors and whether they're excitatory or inhibitory. And then for this, I'm not going to make you memorize these. I would give you these, and then you would just tell me whether it was an agonist or an antagonist. So if you understand how to reason that, then you should be set for that one already. Then the 3 or the 4 columns that are in here might take you a little bit more memorization. But if you need to go back to, well, what was the reasoning behind that and what makes it excitatory and inhibitory, or what makes it ligand-gated versus G protein coupled, you can always come back to this. So I've already given you the answers for these, so I'm not going to spend time to go through them, but what I will do is I will also share with you my answers, like the ones that already have everything put in. I will also share that with you. So if you have any questions about this, feel free to email me or submit it in one of the upcoming questions ones, but I think that should cover it for the neurotransmitter receptors. Again, one of the biggest things is when you go back to your neurotransmitter chart, and when you see this both, that means it's just binding to receptors that give it 2 different responses, because the receptors can have slight modifications that change their effect inside the cell.